He has a very interesting career. Let me tell you, and let me explain to you how we reach Dr. Eng to invite him to give this talk. Few months ago, he gave a fantastic talk in one of the Gordon Research Conferences, one of diffraction, X-ray diffraction methods. Then one of my students, which actually is here, Aranza, told me basically you have to invite him. He's a very good presenter. Then you have fans, Leung, then congratulations. But in addition to that, Dr. Eng is a principal scientist at Atomwise, a leading artificial intelligence drug discovery company in San Francisco. Until recently, Dr. Eng was an associate professor of biochemistry and molecular biophysics at Kansas State University. Dr. Eng's training is in computational structural biology and crystallography. He has studied structure-based drug designs since he was an undergraduate at Harvard University, studying under future Nobel laureate Martin Karplus. Dr. Eng completed his PhD at University of California, Los Angeles, in crystallography and computational biology. After UCLA, he worked as a postdoctoral fellow and staff researcher at University of California in Berkeley. He then worked as a senior scientist and at the Conformational RX under founder, future Nobel laureate Brian Kobilka on G protein coupled receptor crystallography. Dr. Eng is a recipient of the United States National Science Foundation Career Award for Early Career Scientist. Dr. Eng's current research focus on generative models for drug discovery chemistry, automatic computational drug discovery, and homology modeling. Then thank you very much to be here with us. And please, you can start when you want. Thank you very much.
Great. Thank you very much for the invitation. I'm very happy to be able to present to this audience. I've heard so many stories about Unam because one of my close friends and collaborators, Alan Spuru Guzik, some of you may know him. He's a graduate from the chemistry department there as an undergraduate, and we became friends, good friends, when he was just a graduate student at UC Berkeley. Now, after many years, now he has become one of the leading computational chemists in the world. And of course, he often tells me wonderful stories of the experience he had back at UNAM. He's a very proud Mexican. So today I will tell you about some of the recent work that I had been doing in our lab at Kansas State University, followed up with some of the work that we've been doing at Atomwise. So most of my career has been as an academic faculty researcher, and more recently, I have transitioned to industry to work specifically in this area of AI drug discovery. Throughout most of my career, my research has been in the area of structure-based drug design, primarily in the areas of cancer, immunology, and infectious disease. In the last 6 years, I have been focusing in the area of machine learning for drug design. In my academic lab, I had a research program that combined both computational and experimental work using computational methods, primarily with X-ray crystallography. So studying and determining structures of drug protein complexes. So today, we will be talking mostly about homology modeling and its applications to drug design. So for those of you in the audience who are not familiar with some of these terms, I will just give a quick overview. So what is homology modeling? So homology modeling is how we model the structure of a protein if there's no experimentally determined crystal structure or cryo-EM structure. So If there is an experimental structure, then that is best. But if you don't, then there are some sophisticated methods to predict this the structure of that protein. Now, these methods primarily work on using the experimental structures of closely related homologous proteins. And then you take that structure, you put the sequence of your particular target onto that, and then you polish that structure through some combination of physics-based or statistical-based refinement. And this actually works quite well for the easiest cases. In cases where there is high sequence identity between your target and its homologs. For example, in cases where your sequence identity is closer to 50% or ideally even 70%, homology modeling, traditional homology modeling works quite well. Homology modeling often still works quite well when you have identity sequence down into the 30 and 40%, but there becomes more room for error. Now, what I'll be focusing on is this new computational method called AlphaFold 2 that has transformed the field of homology modeling. So probably most people in the audience already know about it, but what AlphaFold 2 has done is that it uses a completely different approach to homology modeling using sophisticated deep learning methods. Now, this has brought an unprecedented new higher level of accuracy for homology modeling. Some of the differences is that, one, I said that it uses deep learning. It's trained on the structures in the PDB. So now there are well over 100,000 structures, and it uses information from multiple sequence alignments. So what information can we get from multiple sequence alignments? Actually, it turns out there's a lot, but it's hard to make use of this. So for many decades now, scientists have identified that through multiple sequence alignments, one can find correlated mutations. For example, if there's an amino acid here and an amino acid here, if this one will mutate, oftentimes you will see in the same organism a neighboring amino acid also needs to mutate to accommodate the new packing and interactions of that first mutation. So one can infer that there is a close association between those residues. Now, this is not perfectly true. This is not remotely true all the time. So that's why it makes it hard to take advantage of this data. So it has to be applied statistically. We'll come back to this figure to talk about the actual behind the scenes of how AlphaFold 2 works. But basically, I just want to give you an idea that really this is something much more complicated than previous approaches, and the results have been really impressive. So impressive that after I gave this talk at the Gordon conference, many students and postdocs came up to me to tell me their own personal stories of AlphaFold 2, almost always success stories. Stories like, oh my God, I used AlphaFold 2 and it essentially solved the structure of the protein that I had been working on for 3 years. So 3 years of time condensed into 1 day of calculations. So in many cases, it outperforms traditional homology modeling. And this is especially true for the hard cases, meaning the proteins that do not have close homologs with known structures. Sometimes the performance from AlphaFold 2 is nothing short of magic, where you look at it and then later on there's a crystal structure that's later becomes available, and you see that the RMSD is incredibly low and that the side chains are placed almost identically to that predicted. Really astonishing. It can do things that traditional homology often cannot do. It can predict entirely novel folds. And this is something that we don't quite fully understand, and we haven't, and I'll talk some more about this, is that it can also sometimes predict protein-protein complexes and how they're organized. So it can predict quaternary types order structures. So that's something that traditional homology modeling cannot do. There are methods for predicting protein-protein binding, but this is something entirely new altogether. So the output from AlphaFold 2 can be what we consider almost comparable to experimental quality, meaning that these days crystallographers will often try to use AlphaFold 2 models for molecular placement. So molecular placement is how you solve crystal structures. So after you collect the diffraction data from your crystal, you still need to determine the phases to solve the crystal structure. We use the phases from a homology model, and that the AlphaFold 2 models are good enough in many cases to do this kind of work. It is also used by cryo-EM microscopists to use these AlphaFold 2 models to guide building structures into lower resolution lower resolution microscopy maps. AlphaFold 2 often predicts multiple conformations, and this is because it has been trained on the PDB, and oftentimes the same protein is observed in different conformations. This is both a plus and a minus, and we'll come back and talk about this in more detail in this talk. And finally, it has turned out that the new algorithms that AlphaFold 2 uses for side chain packing are extremely good, that it outperforms traditional methods at this kind of local packing. However, there's still a lot of cases where it gets this wrong. And again, this is something I will go into some detail about. Okay, so that sounds all good. Some problems. Well, one of the problems is that I think AlphaFold 2 has been extremely hyped. Yes, it is wonderful. It is a major breakthrough, but you can see a lot of the releases, especially, okay, I will name them, coming directly from their team, the DeepMind team, that claims that AlphaFold 2 and in the newspapers that says AlphaFold 2 has solved the protein structure problem. Not at all. The models that come of AlphaFold 2 still require experimental validation. We still find that experimental quality structures work better than anything that a computational model can do. So, but it's great. Okay, but it hasn't solved the protein structure problem at all. Sometimes AlphaFold 2 performs more poorly than predicted. So this is the problem, is that most of the time it works so great that you can't believe it, but sometimes, and you don't know when, it fails, and it fails in a way that is much worse than traditional methods. And this is often a failure of many modern machine learning, deep learning types of methods, that they can make a prediction based on patterns that they've been trained on, but if something happens that they don't recognize, then they take a guess, and their guess can be way off. And because of the opacity of modern, complicated deep learning methods, it's very hard to figure out exactly what went wrong and why it's doing this. It becomes a research project in itself. So it can make very large mistakes not made by traditional methods. And the one that my team and I have observed is that there are register errors where, for example, an alpha helix is completely shifted by a turn in the sequence. Number 3, this has also been thrown out especially on social media, on the other hand, by some scientists who criticize, and this is partly a response to all the hype about AlphaFold 2, that criticize AlphaFold 2 and show you, oh, look, this is the output from my AlphaFold 2 run, and they show you what we call spaghetti. So the spaghetti, well, it's because AlphaFold 2, like almost all homology modeling methods, still is very poor at predicting, or completely fails, cannot predict long, relatively unstructured loops. And there are regions that are just intrinsically flexible and don't have a well-defined structure. So obviously those cannot be predicted in any meaningful way. Okay, there are some questions though. So we mentioned that sidechain placement. In many cases, sidechain placement by AlphaFold 2 outperforms traditional methods. However, and this is something I want to get into, is that sidechain, it is not enough to just say, look, AlphaFold 2 predicted the structure of my protein. The fold looks great. The RMS, the C alpha carbon RMSD looks great, but there can still be critical errors in the sidechain position. And I think that has been overlooked. And 5, this is something very important. So because of the relatively small training data set available for membrane proteins, AlphaFold 2 and others homology modeling approaches often does not work as well for membrane proteins. So be very careful there. It's surprisingly, it works quite well, but generally better than traditional methods, but still fails a lot. And when it fails, it can fail catastrophically. Okay, so a lot of this talk is about pragmatic a pragmatic way to use AlphaFold 2 and how to think critically about the results that are coming out of it. So 1, check your results carefully. So don't just believe the powerful, this is true for a lot of computational methods. Okay, the computational methods says it gave me a structure with these incredible statistics. Okay, the statistics look good. They're great to publish in your paper and in a table, but look carefully at the results. It may not, it can fail. It might look great overall, but in the region that you're interested in, it might be wrong. 2, why not do both? Use AlphaFold 2. Yes, it works great. But at the same time, also use a traditional homology modeling method and compare the two and see if there are significant regions where they significantly differ, and see whether AlphaFold is really doing better or maybe it's doing worse. Okay, so now let's dive a little deeper into how AlphaFold works. And then that way we can understand why it works so well and why sometimes it fails. So we already know a lot about the many cases where it works great. I am interested, especially in cases where it doesn't work so well, so that we and other scientists can build and improve upon it. Okay, so when it first came out and it was released as code and it was released in press releases, but it took a long time before the paper and the code was publicly shared. And when people were and now it's publicly available, there are many web servers that will run it for you, but it's a very demanding calculation. So you can do this now. At the EMBO website, they have pre-calculated AlphaFold 2 structures for all human proteins and many other proteins of interest. So you can go there and just download it without doing the calculation. So that's great. People were a bit surprised that there seems to be no why does AlphaFold 2 work so great? It does not find any radically new information that we didn't know about. So that's a little bit surprising. What it does is that these machine learning methods and this combination of structural modeling, of traditional structural modeling, and using the multiple sequence alignment information, this machine learning framework is really good at optimizing and squeezing every last bit of information from all of that data. And this is generally demonstrates the power of machine learning. Machine learning provides a computational mathematical framework for handling large amounts of heterogeneous data and being able to make the most out of it. Okay, so I want to get dive a little bit into the basics of neural networks and deep learning. So what is going on? Why does deep learning, at least hyped in the media, hyped in the research community, why does it seem to be able to do things that traditional methods cannot? The basics of it are relatively simple. The implementations can be very complicated. So what a neural network does is that it's a connection of nodes, and each node calculates a certain function from prior connected nodes, and then that's how you get your neural network. But what it's really doing is that the neural network acts as a mathematical universal approximator. That means it can approximate and represent any function. So this isn't that new to those of you who have studied math and physics. So we have lots of different kinds of functions like this. We have Fourier series, we have power series, we have Taylor series, for example. And each of these kinds of series can be used to approximate functions and are used a lot. So this is a new way for approximating functions. It works really well because they're very easily computable, and it tends to transform. This is where it gets complicated, and we don't fully understand why it works as well as it does. That these neural network methods tends to transform your problem into a different mathematical space that is smoother and easier to apply derivative gradient-based methods to find optima. Okay, so the more sophisticated and deeper and larger your neural network, it has increased capacity to represent more sophisticated functions such as an image, sophisticated functions like your protein structure. So in many ways, this is an extension of traditional probabilistic and statistical methods. It's really not that new at all in many ways. And it's a lot of the topics in the machine learning research and the literature should be familiar to many of us who work in structural biology. So we are facing issues with global and local optimization, issues of cross-validation. So for crystallographers, this is looking at something like the R-free and how do you hold a secret test set that the model is not trained on, and then that way you can test whether your model is biased or not. And this happens a lot in machine learning, that you can get an overly biased result. So you're approximating a complex function. So I mentioned that this is similar to using Fourier series to actually approximate and actually build a three-dimensional image in X-ray crystallography. So we have seen a lot of these kinds of computational methods before. So some particular issues regarding machine learning to science. So essentially, you can think of it as a very sophisticated form of multidimensional curve fitting. So as we all learned from our earliest classes, curve fitting, you need to be careful about what kind of curve you're fitting relative to the number of data points. So if you only have a few data points, you can fit your data point with an arbitrary number of lines or curves. And it is very easy to overfit your data. So with machine learning, what you need is that you need large, and I should also add high quality data sets. So the larger, the better. In many cases, we're talking about data sets with at least tens, hundreds of thousands, millions of data points. Modern machine learning, at least the advanced methods, don't work well for problems where you have 30 or 40 data points. I mean, there are many ways that it can still work, but that's not what a lot of people are doing these days. And that's not what AlphaFold 2 is doing. AlphaFold 2 uses this large PDB data set and these large genomics data sets. It would not work, period, if we had tried this, let's say 10 years ago or 15 years ago, when our data sets were much smaller. So deep learning can exploit nonlinear fitting to approximate very complex functions. So one of the most serious issues and limitations of these kinds of approaches when we apply them to scientific problems is that in many cases, we don't have data sets that are in the thousands of data points or millions of data points. For us, data is expensive and slow to come by. Extra data point can be a whole day or days of work to do experiments. So I and other people are trying to develop new machine learning methods that are more based for uses for scientific applications where we have fewer data sets, but they're constrained by certain scientific rules. So for example, we know that these data points must obey certain mathematical properties and physics properties. In contrast, a lot of the work done in machine learning has been by these giant tech companies like Google or Facebook, etc. And they've been using it on large data sets of images or text. And those, they can easily accumulate data sets that are in the orders of millions or even hundreds of millions. Now, what they've learned, and this is very impressive, is that modern machine deep learning methods continue to learn and improve performance as you increase the amount of data. So it does not plateau. So that's great. So this is something that you do not see with traditional statistical methods. And so what this means is that in areas of science where you have this kind of exponential growth of data, I mentioned the PDB, of course, a big data set now is genomics, that this is a case where it becomes more and more promising. We see this now, we're starting to see this now with cryo-EM structures. Not so long ago, it was they weren't so common and they were a novelty. Now they're everywhere. Almost it seems like every single issue of Nature or Science has a cryo-EM structure. A particular interest to me are the structures of membrane proteins. So it is underappreciated that about 50% of all drug targets are membrane proteins. But for those of you who've worked with membrane proteins in the lab, they're a real pain to work with. They're hard to express, hard to purify, hard to keep stable, darn hard to crystallize, hard to do assays. But we've been making a lot of progress, and we can see an exponential growth in the number of structures. And of course, this has been helped by the power of cryo-EM, so you don't need to crystallize these darn things. And cryo-EM also allows use of working with smaller amounts of protein, that we can now see a large growth in the number of membrane proteins available. So hopefully we will see better predictions for membrane proteins within a few years. So how does AlphaFold 2 work? So here's that diagram that I had showed you earlier. This comes from the original AlphaFold 2 paper. And I will just go over this a little bit. Won't get into too much detail. So basically, as I said earlier, it takes your input sequence. So that's all the information it needs is your input sequence. And then it takes it into two branches of analysis. One is it looks at genomes and it calculates a multiple sequence alignment. So again, the multiple sequence alignment gives it a way to find all these correlated co-varying mutations and infer that some amino acids are more likely to be close to another. And then at the same time, it goes into the PDB that it's trained on, and it looks for patterns of parts of not necessarily your whole protein, but small regions of your protein that are found in the PDB. And this is the magic complicated part, where this goes into a certain deep learning module called a transformer. It's a bit complicated, so we won't get into that. And it takes this, and then it outputs a representation of a model of the pairwise distances between the different atoms. And then it creates it models a structure out of this. And then this gets fed back to the transformer to improve the multiple sequence alignment analysis and the structural modeling. And then it recycles this 3 times and eventually gives you the output that some of you are familiar with by now, where it gives you a series of structures, and they are colored regions of high confidence and low confidence. Please pay attention to that. So the high confidence parts really are high confident, and the parts that where it says low confidence or no confidence, yes, that's exactly what it says. So now let's look at some case studies of different proteins that our lab has studied, both at Atomwise and at my university. So here we see an enzyme with known structure, and we compare it to its AlphaFold model. And you can see that the secondary structure elements are really pretty much modeled perfectly. This is about as good as it gets. But if you look at the loops are off. And well, I told you before, it's hard to model loops. So it depends on how important these loops are to the function of your protein. Sometimes they're not that important. Sometimes they're the enzyme active site. So pay attention to that. Here's a big failure: insulin, one of the earliest crystal structures. Why does it fail on insulin? Well, it's because as of right now, AlphaFold 2 does not know how to handle disulfide bonds. and AlphaFold 2 does not know how to handle post-translational modifications. So this is something that might change in the future, but beware of that. If your protein is held together by disulfide bonds, then boom, don't expect too much. Okay, and here's a case where it just completely fails and we don't know why. So here is an enzyme that one has expects that we don't know the structure, but based on predictions and some experimental work, that it should have a folded globular structure, a well-defined structure, but AlphaFold 2 can't begin to do anything with it. Let's look at some more specific cases. These come from my lab. So one of the proteins that we've been interested in for a long time is estrogen receptor alpha. So this is the primary receptor of estrogen in humans. And we are interested in it because it is one of the most important breast cancer drug targets. What we in particular are interested in is that when women are women with breast cancer, when treated with antagonists to the estrogen receptor, sometimes, in many cases, over time, as the cancer develops, the receptor mutates and becomes more resistant to the drug. And so what happens is that the cancer will eventually relapse, and that's not good. So what we were interested in is trying to come up with new drugs that would be effective against some of the most commonly found mutations. And so we wanted to use AlphaFold to predict the structure of these mutants. Now, these mutants are just single point mutants. So they are expected, and now there are crystal structures of them. They basically have the same overall fold, and the only differences are relatively small. But we wanted to see how AlphaFold works on predicting point mutations, which you would think is the easiest case. And what we can see here is that it is, and we and others have seen that this is a case where AlphaFold is not very reliable. It is not very reliable in predicting changes in single or simple point mutations. Here you see, in this case, let's just focus on A for now. In purple is the crystal structure of the wild type receptor, and in yellow is the AlphaFold 2 model. And again, if you look at the secondary structure placement, it's almost perfect, except this one part. So you can see that this last helix is in completely different orientations. Unfortunately, that turns out to be the most important helix in the entire protein, because that helix, the reason why is that it does take two different positions depending whether it's in the on or off state. And AlphaFold 2 is not, it's a computer. It's not smart enough to infer knowledge and significance of these states. It has been trained on the PDB, where there are multiple states conformations available. And this is something you'll see. It guesses wrong. Oh, it can't guess. It just makes some kind of guesses about the state of the conformation, and it can put it either in the right or wrong conformation. And of course, because it's the critical helix, it will get it. It can easily be wrong. So pay attention to those parts of your structure. And this has huge consequences. If it gets, this is actually another part of the model. It is shown here. This is actually the drug binding site. So again, the secondary structure placement is great. However, there's this one loop that takes very different positions in the crystal structure versus the homology model. And the incorrect placement of this loop completely blocks the drug binding site and makes drug docking types of studies impossible. So in the modeled structure, the known drug cannot fit in there. So that's a total, so statistically, the AlphaFold model looks great, but you can't use it for any real work because of that. Here's another case. We're looking at PTP, protein tyrosine phosphatase 1B, studied for diabetes as well as cancer. And again, you have an issue where you can see that the overlap is almost too good to be true. But there's this one caveat, is that there's this one loop right here, and it takes one conformation in the open form and one in the closed form. And it's only in the open form that you can bind an inhibitor to it. But AlphaFold 2 models it in the closed form. And in the closed form, if you use that for drug docking types of studies, then again, it will fail for you. Here's another case like this, where if you look at the insulin receptor tyrosine kinase, we can see that again, it captures the overall fold of the kinase very well. But there are, in all these kinases, they have a conformationally varying loop, and that's hard to predict. And this varying loop interacts with the ATP binding site, which is often also the inhibitor binding site. So because this loop is hard to predict, it can be predicted sometimes, but in this case, it doesn't do so well. This also makes it much more difficult to study drug interactions. You see that when we do docking with the crystal structure, we get fairly good scores. The more negative, the better. And when we do the same docking with the AlphaFold structure, we get very poor scores. -6 really means that we can't find any compounds that would dock to that structure. Okay, transitioning to some of the work we'll be doing at Atomwise. Let me give you a short introduction to what we're doing at Atomwise and our technology. So it's been a lot of fun transitioning from academia to industry. In academia, we're kind of working in small groups with very low tight budgets, and we can't really, I can't really do the kind of work I dream of doing because we don't have the budget and the scale that we want to. And what I really want to do is develop methods that can help develop drugs that can go out and help people. And so what we're dealing with is how to attack this problem of screening vast chemical libraries. So in the very recent years, the number of libraries, chemical libraries that have been commercially available has now risen into the billions. So these are billions of compounds you can order from companies, and they're not very expensive. And now that number has gone up to over 1 trillion. And basically, it's been going up by almost a factor of 5 or 10 every 2 years or so. And so now we're getting into numbers where it's very hard to do computational work when you're talking about billions and trillions. How do we search these massive libraries? I mentioned my good friend Alana Spuru-Guzik. We have been collaborating in the last few years on some of these problems. For many years, he used to give a talk about billions and billions of molecules. That was literally the name of his talk. Maybe he even gave this talk at UNA. But now we're beyond that. Now he needs to change his title to trillions or quadrillions of molecules just to keep pace with the times. And so what we have done at Atomwise is that we have developed methods that can scale up to screening trillions of compound libraries. So here is one case study that to illustrate one of our success stories at AlphaFold. So I showed you many cases where you got to be careful with the results of AlphaFold. So we're studying a protein phosphatase target that I can't disclose. This one is human. There's no crystal structure available for this particular protein phosphatase. However, it does have a near homolog with a crystal structure. This homolog is 40% sequence identity, meaning that we should be able to model a fold that's fairly close, but you can't be really accurate in a lot of the details. So what we used AlphaFold to create several models. So that's one thing we like to do is we don't just use one output from AlphaFold 2. We use an ensemble. I believe the number is 5 to 10 that we use. And we do our studies modeling against this ensemble of structures. And we can see that they still are closely related to the homolog crystal structure, but with some variation. And again, the overall fold is probably correct. For phosphatases, so there's a large pocket for binding the phosphate metal ion as well as a peptide substrate. So that is the conventional binding site. So we know what the binding site is likely to be. And then what we do is we run our technology where we use deep learning networks to score. We have technologies that accelerate and try to prune the library so that it goes from billions down to a more manageable number. And then we have deep learning networks to more accurately score the compounds. And what we usually will do is we'll test, depending on the scale of the project, a few hundred compounds at a time. So these compounds are tested, are synthesized, and then we have been able to identify 37 weak hits. Very weak, but sometimes these weak hits can be good starts for a drug campaign. Just with 1 or 2 rounds of optimization, you might be able to get these into something much better. And 4 hits right away, just from a virtual screen that have fairly promising activity. So I think this is considered pretty good, again, considering that we had no crystal structure to start with. So this shows that if you do this the right way, AlphaFold 2, you can use it for drug discovery. And I think one way to do this is by the use of ensembles so that you can capture these different conformations, and hopefully at least 1 or 2 of these conformations will give you the one that is druggable. Okay, so in summary, what we would need to do is we need to use some new metrics. People had developed metrics, but they're not widely used. We still say the quality of a model is based on the C alpha RMSD. And this is something I think this is still useful, but we need more high detailed, high resolution kinds of metrics. We need to know not just whether the C alpha RMSD is correct, but are the side chain placements correct? Are the loops correct? So we need to look at those areas. Especially, we need to focus on the areas of important to us. Doesn't matter if the fold is correct, if the enzyme active site is wrong, the drug binding site is wrong. There are many scientists now that are looking at and have already developed new methods which which polishes the AlphaFold output, or develop a new method that's similar to AlphaFold, but with more sophisticated refinement using physics-based or statistical-based methods like MD simulation to get slightly better results. So I think this is promising. In the very near future, we're going to see gradual incremental performance by that, and that's a good thing. So we see that AlphaFold generates alternative conformations. That's really cool, actually, but it also can be a problem. You need to think about which conformation is the one that is most likely to be relevant to your case. I haven't talked about this in detail, but AlphaFold 2 has shown success in predicting protein-protein complex interfaces. So this is something that was somewhat unexpected. The reason why this works is that a protein-protein interface packs only a little bit differently than intramolecular interfaces. It's still about packing. Okay, so the work at my university was led by graduate student Yezo, who has recently graduated and has taken a job at a biotech company in Boston, following up and doing much of this similar work. So for the students and postdocs out there, yes, there are many jobs available for people working in this field. So that's a very important message for you. At Atomwise, the work was led by scientist Aram, and my academic work was sponsored by various US government agencies. A lot of the tech industries also interested in working in this area now. So people at Intel, NVIDIA, Microsoft, Google, etc., all have significant investments in developing new computational strategies and resources for biomedical and drug discovery research. Thank you for your time. I'm happy to take any questions.
Wow, thank you very much. I think you just give us a very interesting and educative talk. I have two questions and a comment. Then the first one is, how the correctness is calculated in an AlphaFold 2 model depositing the PDB? Because as you explained, it's not the same if you check the model with the experimental data available, or if you try to model a membrane protein. And then I think that my question is, how sure you are of the correctness that the PDB is assigned to the models that appeared several weeks ago in the PDB?
Yeah, you should be careful with them. I think this is an area, this work has really made us question many things and has opened the eyes of researchers that, hey, maybe we need some new metrics, that maybe our old metrics are not good enough for a lot of this kind of research. So yeah, that's the whole area of research there.
Okay. The second question is, when you have these loop problems, as the one that you show us, in which you close the active site completely, have you ever tried to do molecular dynamics to try to produce an improved model to work with?
We have not done that. Other people have published studies on that before. In the old days, right? Because sometimes people are interested in opening or closing pockets. And the thing with molecular dynamics, that's why it's interesting. You never know what you'll get out of it, whether it will open or whether it will close, and whether it does this in a time frame. In the biochemical time frame, we don't know until you can do an experiment, but it's hard to predict whether this opening closing happens on the order of tens of nanoseconds, or this might take something like microseconds, which would be very hard to model.
Okay, and the comment is, when you are in the field, or after you listen a presentation like the one that you gave us, I think that the idea that you finishing is something like artificial intelligence basically rocks, but it will do better with more and more experimental data. But if you talk with people, some of the authors of AlphaFold 2 or people producing news from science, it seems that the message should be, all is done, don't worry in experimentals. Then how to do with this reality? I feel very, very, very very strange with this feeling, because even in my institute, people said, well, you don't need to do more experimentals on structural determination because AlphaFold did it and it's solved. And it is completely false.
That's right. I agree with you. So for those of us who work on this, and I think if you're talking about to people in in the drug discovery industry, in industry working on this. No, we would definitely prefer to have a crystal structure than an AlphaFold model. I mean, if you can get one in a timely manner. Now, getting a crystal structure can vary from being relatively easy that you can do within a matter of weeks to being almost impossible. So, so AlphaFold gives you a nice option. You can do it, calculate it for free. So let's do both. But ultimately, the experimental model is what we need. That's the ground truth. But yeah, I think there is this misunderstanding, especially among some people who are outside the field of structural biology. I think they have been misled by a lot of the hype coming out of DeepMind and some of the general press that, hey, AlphaFold works so well that we can deprioritize, and then that's what I worry about, that it'll make funding bodies and university administrators say, oh, maybe we don't need to hire so many of these very expensive fundamentalists, right? Let's just do the cheap computer stuff.
Well, thank you very much. I'm sure that more of my colleagues have questions. Nina?
Hi, thanks for your talk. It was eye-opening for many things. And I have questions about the miracle of having a lot of data. So what happens in the context of artificial intelligence when you have lots of data, but there are inconsistencies between?
Yes. So that's why I said lots of data, ideally good data. Ideally good data. I mean, this is not as, this happens all the time. So for those of us in drug industry, what we often have to do is integrate lots of different assays that were performed by different labs, and they all are performed by a slightly different, and they even have different kinds of output. You have to find a way to try to integrate the data and make them make them in a statistically sound, significant way. Yeah, it's challenging. There's a whole field of data science doing this, and it's not so clear how to do this.
I figured. And also regarding these huge pools of molecules that you can test when you do screening, could you give us a rough idea of how is it that you trim from 33, what was it, trillion to 500? What do you look at?
Okay. So we start with the 30, we can start with simple filtering rules. For example, we don't want molecules that are too big, molecules that are too lipophilic. And
okay, so Lipinski.
Yeah, Lipinski-like type rules, but that's, everyone does that. But a little bit more, the more sophisticated kind of filtering is we look at different kinds of shape filtering or chemical filtering. So for example, we think that the binding pocket is like this. So we expect a certain shape of the molecule, and you can do shape filtering, which is cheaper than doing a full docking type of filtering. And you can do even sub-shape filtering. We know that a certain part of the molecule already is not likely to fit in there. And so by that, you can there are specialized algorithms that can quickly eliminate from trillions down to, let's say at the end, you end up with a million or a few 100,000. And then you can do more traditional methods to analyze those.
So that would be something like first building a pharmacophore and then using that to filter?
You can also do things like that, yes, by building pharmacophores and combining them with shape models. A lot of combining 3D structure-based with more traditional ligand-based types of models. There is quite a lot of literature published in the last 1 or 2 years about how to working with these ultra large libraries that describe specific algorithms.
Right. And regarding you said that you asked AlphaFold to give you not just one model, but like 10.
Right.
So say for the estrogen receptor that has 2 conformations, do you happen to see in your universe of 10 that some of them are in the open and some are in the
Yes,
closed,
usually.
somewhere in between that doesn't really make sense?
Yes, that's right. So it depends on what's in the PDB. So usually for most of the proteins that we're interested in, there are structures both in the open and closed conformation, as well as various intermediate or maybe even non-relevant conformations. So all of those are trained. AlphaFold is trained on those, and it can give you these different kinds of conformations, and you can even force it to say, I don't want this specific conformation, give me an alternative one.
Right. My experience with AlphaFold has been really bad. I mean, I have caught it telling me stupid things 5 times already. So I really use it sparingly and always in combination with something else.
Great.
So,
yeah, I mean, that's kind of why I gave this talk, because some people will say this is a miracle, it's changed my whole life, and other people say the results are ridiculous.
Yeah, at least that you should look at it. I taught a class yesterday and people were just like, okay, I'll just run my protein through AlphaFold. It's like, hang on a second, it doesn't even get rid of the signal peptides. So
that's right.
Wait, no?
That's right. Yeah, it's not smart. It's ultimately still a sophisticated piece of software. It doesn't incorporate human expertise.
No, well, it is machine learning and it learns from huge data sets. That's something that you cannot do explicitly. It has to do it. The magic happens in between all these layers of neurons, no?
Yes.
But still, it is only as good as the thing you trained it with.
That's right.
And that's what happens with the membrane proteins. You have a data set that is this size, where your predicting power is this size also. That's it.
That's right.
So thank you very much.
Oh, I'm curious, what are the use cases that you're looking at that are where AlphaFold performs so poorly?
I tried with a protein that is a hydrophobin. It falls into this very nasty class of proteins that has lots of disulfide bonds.
Disulfide bonds, okay.
No, but wait, what struck me is that the sequence that I inputted is in the PDB. And AlphaFold was incapable of telling me that it was in the PDB.
That's right.
So yeah. I don't know how that happens. Any self-respecting homology modeler will tell you, please do your homework. It's already in the PDB. Well, AlphaFold is so sophisticated, it forgot.
Yeah, I've seen some cases like that. And that's why I recommend running AlphaFold at the same time as running a traditional homology model. So, because there are some cases where it just fails and I don't know why.
Yeah. Another one was a single chain antibody, these SCFBs. And I got a whole collection of interfaces between the two domains.
Fascinating.
And I have no idea why, because most of the things that are deposited in the PDB are the classical Benz-Jones surface.
Yeah. You could write a whole paper on just that, on this observation.
Oh, really? Okay. I was this close to disposing of it.
Oh, yeah. Well, I mean, the antibody modeling, that's a whole big business in the biotech world. So
yeah, I know.
Yeah.
Right. So thank you very much. I'm going to have to run, but it was a pleasure listening to you.
Great. I'm happy to take questions by email too, for if anyone has questions later on.
Thank you. Thank you, Nina. I have another question once that I listened to the previous one. I mean, I'm sure artificial intelligence programs are going to be as best as the data sets are used to train the program. But let's be frank, the PDB is an heterogeneous collection of different levels of quality experimental models. Then what about, I'm not sure if people have understand this problem and try to train AlphaFold instead of the full PDB to a kind of curated PDB in order to improve the quality of the predictions.
That might work. It's hard to say. I mean, I think given the nature of the PDB, given the nature of some of our databases, I think, for example, the PDB some of the genomic, different varying levels of the genomics databases are actually can be considered quite high quality in terms of data, compared to, for example, the example that was brought up earlier, trying to integrate all different kinds of assay data into one big model. That's a little harder. But you might see in performance improvement by, like you said, curating and choosing only the best, most reliable protein structures.
Okay, thank you. Carlos, do you have any question?
Yes, I have just a practical question. You said to be careful to check the structure, and I completely agree. But the question is how? I mean, if you have a crystal structure, yes, but if not,
If you don't, right?
How do you do it? I mean,
Yeah. So in many cases, even if you don't know the crystal structure, you can make some good guesses, for example, as to the enzyme active site, or perhaps the potential drug binding site, the areas that you really care about, and getting an idea whether the output makes sense to you as a scientist, whether the catalytic residues are in the right place, etc. So it still takes a human expert. Yes.
It's good for us.
Yeah, we're not out of a job by any means. Yeah.
Does anybody have more questions? If this is not the case, thank you very much for a very nice talk. And let me tell you that there are several people connected through Facebook and also in the YouTube channel. Then let me invite them to send you an email if they have specific questions regarding the field that you gave us. And thank you very much for accepting our invitation and for a fantastic talk. Thank you very much.
Gracias. Thank you very much. I appreciate
De nada.
to this group. Thank you very much.
Thank you, and it's a pleasure to listen people as you talking on these kind of fields. Thank you very much.